Okay, guys, welcome to our lesson on evolutionary game theory. This is going to cover two subjects in conjunct, which are game theory principles and then evolutionary biology. I'm really excited to be presenting this because it's the first lesson in our interdisciplinary lesson curriculum. This curriculum is going to occur throughout the year on a bi-monthly basis. We're essentially going to be covering, topics that our teachers find interesting or career-related fields that we want you guys to explore, and hopefully you learn a lot through these lessons. So, without further ado, let's get started. So what is evolutionary game theory? Well, first of all, I want to define what game theory is. A lot of people think, it's about games, and I guess that's half the picture, but more specifically, it's defined as the study of mathematical models of strategic interaction amongst rational decision makers. Now, this is really important in the field of evolutionary biology, because in biology, you have a lot of individuals interacting all the time. You see, individuals within a population interact, in competition, individuals are interacting. And one of the really things we want to get at is how to define this sort of interaction. It's really easy to explore this, interaction from a qualitative lens by describing it. But how can we study it, using some mathematical model that helps us to understand why certain strategies appear in nature and why others don't? That's really the heart of what evolutionary game theory is all about. And one of the really nice things about it is we can craft these mathematical models by often using simulations. Simulations are a great tool because not only can we define them to some sort of mathematical lens, but they allow us to predict what will happen in an evolutionary interaction in the future. And that's something that I know a lot of evolutionists, want to see, being able to predict what will happen to a population with, said event. So that's why this field is very relevant, especially to the modern climate. So to start off, I just want to play a game. And this game is called Hawk versus Dove. It's a really common game within the field of evolutionary game theory. So what does the game of Hawk versus Dove entail? Well, we start with two types of strategies, and the strategies are Dove and Hawk. The Dove is more of a passive strategy, whereas the Hawk is a more aggressive strategy. And what we want to see is how populations or individuals that employ a Hawk strategy interact with individuals that apply a Dove strategy. We were getting to before that we wanted to find a way to quantify this aggressiveness. How do we do this? And that's where using a game theory aspect actually really helps us. For the first time, we're actually able to see how these populations interact, how their numbers fluctuate, etc. So that's what we're going to be doing right now. The way we're going to be doing this is using a payoff matrix. This is where the mathematical model steps in. You can kind of see that there's a 4x4 quadrant. And the easiest way to think about what's happening is you just assign, what is on the top with the on the left side. So for example, the top left quadrant is just a dove interaction with a dove. The top right quadrant is just a hawk interacting with a dove. And then each of these, numbers or variables inside a box represents an arbitrary score that we give to this type of interaction. The score might, in this example, would be an indicator of reproductive success, or in this case, being able to get a resource because you're more aggressive over someone that was, more passive. So that's what the different types of scores can represent. And you can kind of get the idea that in different situations, the scores will change. And of course, they fluctuate, but knowing some sort of interaction and being able to assign numbers to it helps us to study it a bit better. So that's what we're going to be doing through our interaction. Now, I'm just going to cover one more slide before we head in straight into the interaction. Again, we have the hawk and the dove. The hawk is going to be a creature that kind of displays aggression. And then to give a more real world context behind it, because I think that's really important, it's kind of the person, the creature that, escalates into a fight until it either wins or is injured. Whereas the dove is a creature that displays aggression, but, faced with major escalation, it will run for safety, and it will often try to share the resource if it's, not posed by an aggressive creature. Now, I should actually make a clarification, which I think is really important. In the real world, I'm not talking about, there's hawks and there's doves. I think the best way to visualize what is happening is each of these are strategies that can be employed within the same population. So you can have some individuals that are of a hawk-like nature, whereas some are more of a dove-like nature. And in the same scenario, even though, they're part of the same population, the frequency of hawks and doves differ. I should say there's also limitations with this model, and the limitation is that you can be in between a hawk and dove-like characteristics. You could be like semi-aggressive, semi-passive, and it might change in a scenario. For now, we're going to focus on the two extremes because it will lend us some insights I think are really important for the simulation, and then we'll try to explore that with a more game theory lens as to why those strategies occur in nature. So before we get into our simulation, does anyone have any questions so far about the overall game logistics, about the hawk-dove interactions, or anything along those lines?
Could you maybe explain the payoff matrix in more depth?
Yeah,
Like I understand the V and K, but like so what exactly is V and K? I understand 5, 10, those are all like
Yeah, so right
changing.
now, these are just arbitrary numbers. I'm actually going to show what they mean when I'm using the simulation because you'll actually see how I coded it. But here, I guess, for now, they're just arbitrary scores. V and K, I guess, here's an interesting example because V stands for value and K stands for cost. And this is a similar model that I'm using in my simulation, which you'll actually see. These are all, B, C, and D, I just will say are arbitrary, random, interactions. So don't worry about that too much because we're going to actually be able to manipulate all of these so we can kind of see how populations, fluctuate when we try to change our simulation in different ways. And yeah, and lastly, I should mention, I think I mentioned this, but the score in each quadrant is also an indicator of, reproductive success, whether that trait is going to, or strategy is going to carry over to the next generation. So that's why the higher the score, the better. So let's move on to a simulation. So I'm going to first describe a simulation as to what composes it before we actually start the simulation. So what I set up is essentially just a blank screen. You can see there's a field which will spawn a hawks and doves. And we also have a graph. I just use a graphing API, and the way it works is it essentially takes in the number of hawks and doves present on the field and it records it in a graph. And every generation, what we do is we use the payoff matrix. We essentially put individuals against each other, calculate their reproductive success based on the scores or the quadrant values that we manually assign, use that to determine the next generation of doves and hawks, and then redo the simulation. So every time we're going to see actually the numbers of hawks and doves fluctuate based on game theory, the payoff matrix. So over here is probably the most important script. Here we can kind of see what's happening. The way I assigned it is I assigned it 4 values for the 4 interactions. So dove means what happens to a dove if it is interacting with another dove. And 0.5 indicates it's sharing a resource. Whereas when a dove is interacting with a hawk, maybe it gets a bit less of the resource. In this case, it only gets 1/4. And then if we continue along these lines, what we're going to see is hawk dove is 0.75 because the hawk is going to hold the majority of the resource. But when a hawk interacts with a hawk, we can say, okay, they're going to split the resource, but they're also wasting energy in terms of, because they're more aggressive creatures. And as a result, we have to subtract that from the score. And that's why I said the hawk off payoff is 0.25. I'm just going to quickly check chat because I see a lot of things happening on chat, but okay. Just wanted to make sure that there were no questions. Okay, so that's a brief overview of what these scores represent. And now to put them in context of our evolutionary game, we need a way to define what these scores actually mean. So what I did is define a survival percentage and a reproductive percentage. Now the way this works is these scores measure the interaction a dove has with another creature. And based on that, we assign a survival percentage, which is the minimum threshold it needs to be to survive. So say a dove interacts with a dove, they share the resource. In that case, it's going to survive because, of course, it gains 0.5. A score of 0.5 is associated enough with survival. However, the reproductive percentage is 1, which means that technically to have a 100% chance of reproduction, you need to have a score of 1. But now you might be wondering, well, we can't do that because a hawk dove, a hawk isn't going to gain the entire resource. It only gains 3/4 of it. So this score is a bit arbitrary. What it really means, 0.75, or the way I defined it via code, is, okay, it guarantees that a hawk survives. But because it's exactly between the reproductive percentage and the survival percentage, what we're going to do is give it a 50% chance of reproduction. So it's basically proportional to the difference between the reproduction and survival. Say you had something with a score of 0.6, that would mean because it falls between survival and reproduction, we would assign it a 20% chance on reproduction, but you would also guarantee its survival. Similarly, a 0.25 does not mean the creature doesn't always survive. There are times where it will survive because 25% here or 0.25 just means a 50% survival rate. So again, the way I'm doing this is I'm just doing 0.25 over the survival percentage, and that's the true rate of survival. If you're at 0.5, that's guaranteed survival. Anything lower than that, you can divide by 0.5 to get the percentage of survival. And then you can repeat the process for reproduction. If you're greater than 0.5, you can guarantee survival. But the closer you are to 1, the higher the chance of reproduction. So 0.75 is a 50% chance reproduction. Before I start the simulation, does anyone have questions about the overall evolutionary controls, game theory controls, etc.? Okay, we should be good. And now I'm going to move ahead. The last thing to mention is the food quantity. This is actually important because we're going to be manipulating it down the line, and you will actually see that it changes the results of our simulation. Changing the food quantity can actually change the number of hawks and doves or the equilibrium of hawks and doves as we go through generations. So the first thing I'm going to do is start off by really showing what these creatures do. I'm just going to start with two hawks and 0 doves. I just named it passive count and aggressive count. So I'm just going to clear the memory and start the simulation. So right now you can see 2 hawks start, and you can see over time they're just gradually increasing. The guaranteed reproductive success if they find basically a food on its own, but they're guaranteed survival if they interact with another dove, because doves, remember, share resources. Now a really interesting thing occurs. Some of you might actually recognize the shape of this curve. Does anyone know what this curve or the shape of it is called?
It's sigmoidal growth curve.
Yeah, it's a sigmoidal growth curve. Now, if you've been exposed to topics of carrying capacity, etc., you will know that this actually, if you see something in real life that is defined by carrying capacity and it was have logistic growth, and it's defined as a sigmoidal growth curve. But just by using game theory principles and this sort of interaction, we can actually generate that sigmoidal curve. So we have an understanding that what we've coded is actually a good way to make predictions about how populations will fluctuate with different food quantities. Because of course, this really nicely showcases a natural sigmoidal curve just through a simulation. So that gives you an idea of how doves interact. Now, something to mention is, in this case, there are 100 food resources. So it makes sense that by definition, there are, 200. If you scroll, I can maximize. But it makes sense that there are 200 doves because doves can share resources. So in this case, 2 doves can be sharing 1 food to survive. But beyond that, if you have 3 doves and a food resource, the 3rd dove will die out because it cannot take that resource, or that resource will be inadequate, which is why it hovers around 200. One thing I should mention is all simulations come with their limitations. Technically this value is exactly 200. In real life, it's only going to what's going to happen is it's only going to approach the carrying capacity. It typically won't, just stay at the carrying capacity. There's much more fluctuations in real life. But because we're using a simulation that just defined by game theory principles, it can't distinguish between that and real life. It just gives you a good overview of what you might expect, like a sigmoidal growth curve. So now let's actually move on and keep, this idea of 200 in the back of our mind. What I'm going to do is change the passive growth count. So I'm going to exit the simulation. And I'm going to change the passive growth count to 100. So we have 0. So we have 0 hawks. And now let's, put 2, well, I think I switched the order. We have 0 doves and 2 hawks. So in this case, we're switching our starting orientation. I'm going to reset the scene one more time by clearing it. And for now, we're going to keep the same game theory percentages. The nice thing about doing it as this way is you don't have to change it every time because they're all saved and we have the same food quantity. So now let's play it out and see what happens. So we see that in the beginning, you'd expect something really similar. Even aggressive creatures are going to reproduce if they get a food all to its own. But the thing happens is when they interact. When they interact, it's a bit different because when they interact, they actually spend more energy interacting since they're more aggressive. This means they're often fighting with each other. And what you get is much different than a typical sigmoidal growth curve. We often think, a sigmoidal growth curve is everything we should expect, if we have a great, a carrying capacity in an organism. But sometimes we don't realize that competition isn't always, streamlined, isn't always going to give the same model. Just by changing how aggressive creatures interact, which can influence their reproductive success. Some might be fighting with each other, or wanting to gain more of the resource, you can see the curve is much different. And what's more important is the carrying capacity, we call it, has changed. By making the creatures more aggressive, it makes sense that, in this case, the carrying capacity originally was 200, but with the same amount of food, it's actually about half the size, which is a really interesting phenomenon because it shows that, you might be thinking that aggressiveness is something that's typically beneficial, it's a more selfish trait, but allows you to have a greater success, but it can actually be detrimental to the success of the entire population. In this case, it actually diminishes the total number of hawks that are going to be present in our simulation. So you can kind of see this is what happens with hawks and doves. Now, what happens if we combine the two? That's really the question we want to answer. How will the curve look like? How will the populations fluctuate, etc.? So let's move on to that. One more time, I'm just going to clear up little breaths. And in this case, let's just assign the numbers to be same. We have 2 hawks and 2 doves. Before I start, does anyone have any predictions? And I will say one thing to look at when making predictions are these values over here, because they really dictate what our simulation is all about, how the evolution is going to work in terms of survival and reproduction. Does anyone have any idea of what creature might win?
Probably the hawk because they're more aggressive.
I see. Okay, you're going with the hawk. I like that. Does anyone disagree with that? Okay, so I'm gonna say.
Wait, Arnav, what do you mean by win?
So by win, I thank you for making that clarification. By win, I simply mean which one is going to have the higher population at equilibrium. Typically, you see that eventually it fluctuates around a specific, it might reach a carrying capacity, etc. So there will be a moment where the population has reached a state of dynamic equilibrium and the populations are relatively the same. They won't show major fluctuations. And at that moment, which would the hawks or the doves have the higher concentration of population at equilibrium?
I mean, to me, it makes sense that you'd probably have a higher dove population purely because the predator versus prey dynamic usually tends to have a higher prey count, or the or the population of hawks technically wind up falling off.
Don't they both eat the same food though? It's not like the hawks are eating the doves, are they?
Oh, it's not the hawk. I thought the hawks are eating the doves.
I guess thanks for making that point. The hawks aren't necessarily eating the doves; they're just more aggressive creatures. So that means if a hawk and dove approaches the same food source, remember the hawk is naturally more aggressive. So what happens is we default to the 0.75, 0.25 rule, which is the hawk survives and there's a 50% chance of reproduction, and the dove has a 50% chance of just surviving and a 0% chance of reproduction.
Wait, so Arnav, if your percentage is exactly 0.5, then there's no chance for you reproducing, right?
Yeah. That's okay. The disadvantage of the dove strategy, which is you share resources with doves, but as a result, you can't.
Oh, I see.
The only way a dove could theoretically reproduce is if at the beginning it gets the food source all to itself. So if the dove or hawk is, I guess I should have mentioned this, but if the dove or hawk is, not interacting with another creature, it makes perfect sense that they reproduce. It's only when the populations become higher that the game theory principles really come into play, because now you have a lot of interactions happening. Okay, so I think I heard both hawk and dove. So thank you guys for your responses. We're going to see what happens. Unfortunately, my Zoom thing is getting in the way. So Yeah, I'm just going to quickly clear the memory and just make sure. So we're going to have 2 passive, 2 aggressives, so 2 hawks, 2 doves, and then 100 food quantity. So let's see what happens. So we're going to start off. And at the beginning, things are going to be the same because they're not really interacting a lot. So let's see what happens. So it seems right now at the very beginning, it seems the aggressive creatures are, dominating in terms of, and it kind of makes sense. The aggressive creatures are doing much better because they're going to dominate over the dove creatures. So let's see what the equilibrium shifts to. I'm just going to let it go for a little more. We can see with time that as of now, it doesn't seem to have a major change. But right now we see what's happening is they're actually getting really close together. So we saw initially what happened is the aggressive creatures actually shot up. But with time, the difference is actually diminishing. And if we run the simulation a bit more, so right now is something that's really surprising. They actually intersected. We saw the aggressive creatures have the lead for a long time, but over time, now the doves have caught up. And let's try to make some sense of what is happening here. So it turns out, based on this mathematical model, that the equilibrium is exactly 50-50, based on the game theory principles I set, which is exactly what we're seeing. And I heard arguments both ways, and both of the arguments I actually heard for each case apply in different scenarios. And we're going to also be looking at those different scenarios. So let's try to understand what is happening. Actually, does anyone want to guess why in this case, the aggressive population shot up, but with time, the dove population gradually matched or leveled out the aggressive hawk population?
Wait, Arnav,
Yeah,
can I ask you a quick question?
yeah, sure.
For an actual lecture, would you provide people the source code in a zip file so they can look over it themselves?
Yeah, sure. I think I wasn't planning on doing that, but now that you say that, I have nothing against that. So I think I might just upload the Unity file to GitHub. I know I accidentally stopped the simulation by accident, but we saw that the aggressive population was dominating at the beginning, and then they panned out. Does anyone have any idea why this might be? Or does anyone want to try to predict
Yeah.
why? Yeah.
Maybe the hawk population started growing, so they started competing against themselves, and then maybe
Yeah.
the doves were able to overcome that.
Yeah, actually, that's literally the so at the beginning so you saw at the very beginning they were both increasing at the same rate. Then the hawks took control simply because now the hawks were interacting with doves more likely than they interacted with other hawks. So that as a result, the hawk population immediately spiked up. But once it spiked up to a point, now it was interacting with so many hawks that the hawk population started decreasing, and the dove populations would gradually increase. With over time. So it's this interesting mix where you see the initial state is much different than the end state. You have to give it time because that's why, a lot of populations, you can't really predict what's happening instantaneously because you might know the setup. Here we knew the game theory controls, but it was really hard to see, take a snapshot of what's going to happen after 10 generations versus after 100 generations. Because only when we let it play for a long time do we actually see what the equilibrium happened to be, which was a perfect 50-50. So one of the things I do want to mention in my PowerPoint is a way to envision why the equilibrium is where it is. It might be really nice to say, look at a simulation and be like, okay, we ran this for this long and we got an idea of what the ending the fluctuating concentrations were. But the question is, we don't always know that. The question is, knowing some of these, maybe we can assign arbitrary scores based on how we define these interactions in the real world, comparing value with a cost of obtaining a resource, we can come up with some numbers. Can we kind of, derive the equilibrium concentrations of both populations just using these numbers alone without a simulation? And that's something I'm going to be covering a bit more in the PowerPoint. before I get into that, I actually want to just play around with a few more factors I think are interesting to showcase. You will see if I change something. So one thing I could change is actually make hawk versus hoves 0, which basically means, a hawk versus hove, they like fighting each other to the death. They're basically really aggressive creatures. So it's almost like they don't really have a high chance of surviving because they're too focused on expending energy and fighting other creatures and that way when they do get that food, they've already wasted so much energy and it's not going to be good for them in the long term. If I decrease this, you can kind of like I'm not going to even ask the question because I think it's kind of obvious what is going to happen. So I'll just replay the simulation. So again, in this case, we decrease the hawk versus half payoff. So now in this case, hawks have a lower, in this case, chance of survival. So in the beginning, we see everything is good. Hawks still have that, the high thing we were looking at earlier, which is that it's expanding faster than doves. But only by generation 10, we saw that the dove population is now much higher. And around now is when it's going to actually start reaching equilibrium, which is really interesting because it's really easy to characterize hawks as selfish creatures. But you can see even the hawks are much better at, than doves in terms of interactions. Doves only have a 50% chance of survival. Hawks are guaranteed survival and a 50% chance of reproduction. Look at how much that shifted the curve. Like in this case, just by changing the hawk versus hawk interaction, which shows how detrimental being an aggressive creature can sometimes be, you can actually really change how successful doves are in a population. Now, this is like something interesting to showcase, and you can see it will like, I guess I believe the equilibrium is, if you actually math it out, it's the dove population is about 2 times as strong as the aggressive creatures. It's interesting because right here, now this is because of fluctuations, we're only using a smaller population, so there's a lot of fluctuations that can happen. But eventually the dove population will be still about twice as high as the dove population will still be about twice as high as the aggressive population. The interesting thing to see right now is what happens if we change the food source. This is a thing we haven't mentioned. We were talking a lot about, changing game theory principles. A lot of what we saw made sense. Decreasing hawk versus hove is going to change the interaction. And I can do the same for this, but I'm not going to because I think you guys can get a clearer sense of how this works. If you increase the dove versus dove interaction, of course, doves are going to increase. If you increase this, it's going to make it better for doves. And if you increase these 2 values, it's going to make it better for hawks. That's not really the surprising part. The main things we're focused on are the equilibrium concentrations and also how does food quantity affect the concentrations. Before I mention, does anyone have an idea of how food quantity comes into play? What happens if I ran the same simulation with a different food quantity, which changes the carrying capacity? What might you expect?
Probably the same curve, but just a higher derivative everywhere.
What do you mean by higher derivative?
Like it'll be a higher slope at every single point.
Oh, I see. Yeah, pretty much. But one thing I really want to focus on actually is the equilibrium concentrations. What do you think is going to happen between the doves and the hawks in terms of the relative concentrations?
I think hawks would go up, right? Because there's a less food source and they're more aggressive for it and they're fighting for it.
Okay. Thank you for your input. I'm not going to actually say it. I'm just going to actually play the simulation and we can find out. So what I'm going to do is have 2 situations. I'm going to change this back to 0.25. Remember, keep in mind, this was a 50-50. So we saw with, in this case, 100 food quantity that I believe it was 50, like the dove and hawk concentrations were about equal. So now let's change it to, actually, I'm just going to exaggerate it. So I'm going to make it 25 and start with 2 and 2. So you can see right now, in this case, what happens is, in this case, it looks about a 50-50. And that's exactly what someone would expect to happen really. It's not going to really change the outcome of the fluctuation. All that's going to happen is some of the derivatives are going to slightly change. It's actually by changing the food source, it changes the initial fluctuation significantly, but overall the ending concentrations will be pretty much the same. So in this case, if you expect, the hawks and doves to be about the same, you'd expect them to be about the same even with a lower food source, which goes to show that changing the food source doesn't actually change the ability of a strategy to be successful in a population. It simply changes the concentrations. Well, it doesn't even change the concentrations of the strategies in the population. It simply changes the total number of individuals that use each strategy. So the last thing I want to mention is actually that there's this interesting concept about a perfect simulation versus the real world scenario. Of course, we mentioned how we saw sigmoidal curve, a lot of different other factors. I think one thing to keep in mind is a simulation isn't going to be perfect. The entire reason we use simulations is to get a better sense of why things occur the way they do. So one thing I'm really interested in seeing that I want to show you guys is what happens if you have a passive count of 1 and an aggressive count of a passive count of 49 and an aggressive count of 1, which means you have 49 doves and 1 hawk. Now, remember earlier, what happened was when we did this with 100 food source, we started with 2 hawks and 2 doves. They were on the same ground. Now, my question is, what happens if we use the same food source, but we change the starting concentrations? In this case, we have 49 doves and 1 hawk. What do you guys would expect? Do you expect to get the same ending concentrations, or do you expect the results to significantly change because they're biased in terms of one strategy?
I think they'll even out, but it'll take a lot longer.
Okay, I like that opinion. Does anyone have any other guesses? Okay, let's play it. This time I'm gonna remember to clear. Let's see what happens. So off the bat, we know that doves are gonna be dominating. So that's kind of what we'd expect. And think about what's happening right here. It's interesting to consider, but what happens is the doves are going to be increasing a lot faster, which makes sense because there are already so many doves. And doves, vibe really well. But because over time, the concentrations, the game theory principles dictate how simulations occur. Asher was right. Over time, they're actually going to even out. And the really interesting thing to, again, point out is how the initial concentrations are always much more different than you'd expect than the ending concentrations. The initial, like in the first few stages around generation 4 and 6, you can kind of see how it was all dependent really on the starting population. But over time, gradually, it's going to approach that same nature. And this brings up a really interesting point. It's not really easy to tell what's going to happen instantaneously. Yes, we can know the starting populations, but something we never want to confuse is the overall equilibrium of a population in the long term versus what is going to happen immediately. What's going to happen immediately is always deterministic based on the present population, but the equilibrium is always something that's going to play out in the long term. So that's what we saw. Now, we can do one more simulation, which is the other way around. You can see the ending was 83-77, which is about 50-50, kind of what we expect. Now, what happens if we switch it one more time? So we do 1 and 49. Does anyone have a guess of what will happen now? So this time we have 49 hawks.
I think this time I think it'll even out again. Maybe the doves might even go further, a little bit higher than the hawks.
Let us see. So you'll see what's happening here is a really interesting shift. So right now, the doves are taking a lot of time to increase, which kind of makes sense. And I want to actually point to this. And right now they decreased. They barely increased. Now they're increasing again. Now they're increasing significantly. And as they increase significantly, you can see that over time, they're eventually going to get to a similar position. It just took so much longer than you'd expect. And part of the reason is to understand what is happening. The really interesting thing is sometimes when you start with one dove, there's a chance it dies at the very beginning. Now, this is where doing aggressive strategies comes into play. Because of the nature of aggressive strategies, what happens is there's a chance that if there's a low number of doves, they could potentially get extinct. And the reason being is because hawks are already dominating the board, even though the equilibrium favors an equal concentration of hawks and doves, the scenario itself does not. You're literally taking a majority hawks, which do better against doves, and then having a dove, which you're really hoping can reproduce by getting its own food source. But there's a very high chance in that scenario that it could meet a hawk and just die, which is kind of why we saw that there was this really interesting shift. Wait one sec. Sorry about that. Okay, so as we see over time, what happened is now we have the concentrations around being equal. But the interesting thing to point out once again is that in the beginning, it's always deterministic on the initial concentrations. You can kind of see how, because the aggressive creature favored hawks against doves, it's actually really hard for the doves to sometimes increase. You will often see maybe in most, like half the simulations, there's a high chance that the doves actually go extinct in the beginning, which is sometimes contradictory to what you'd expect, which is a perfect equilibrium. So that gives you some insight into how simulations work. They can help us capture what happens at the beginning and ending, but they also allow us to help understand why they happen by seeing the fluctuating concentrations. So I'm gonna now move away from the game and actually talk about more of the mathematics behind it. And we're probably gonna end off on just a general note of game theory. So for the rest of the lesson, I'm just going to use the PowerPoint and go through it. So we kind of did the recap. We used this payoff matrix, which you can kind of see over here. I already mentioned it in the simulation, so I'm just going to move on. One really interesting thing to look at is the prisoner's dilemma. Now, you might be saying, okay, this is a completely different this is completely different from the hawk and dove scenario we were covering, but it's really not. So what the prisoner's dilemma is also something, it's a really interesting simulation within game theory. And the reason I'm bringing it up is because there are some parallels with game theory that I also want to mention apply to evolutionary biology. If for those that don't know, the prisoner's dilemma is a dilemma where you have two options. You essentially two partners who committed a crime go to jail and the police want them to confess. So if both remain silent, they both get 2 years. However, if you like rat out the other person, you get less years and the other person goes to jail for longer, otherwise vice versa. And then of course, if you rat out the other person and the other person rats out you, you get both 5 years of jails. So the dilemma is, it's always in your best interest to rat out the other person to confess that the other person did it. But in that case, you get less years. But the thing is, if both of you do it, that's worse off than both of you being silent. One of the ways we can represent this is using arrows. So this is something we often use in game theory to actually just see how strategies fall into play. So one thing we can look at is, okay, if person A was silent, so if person A was silent, what is person B's best interest? Person B's best interest is to get 1 year of jail rather than 2 years of jail. So we might just go, put an arrow in this direction. And the same thing we can repeat. If we do something like this, I actually think drawing might be a bit smarter. Probably should have drawn. Yeah, we can just draw like this. And then if we repeat the process, we can be like, okay, say we were in these two scenarios and A confessed. In that case, okay, we can see something again. In this case, B's best interest is to also rat out A. I should say confess really means to rat out the other person, not confess yourself. But in this case, you can kind of see both strategies tend towards the right direction. I guess I'll make it black so it's easier to stand out. But if we repeat the process for person B, if we have, person B be the one who's choosing based on person A, we can see the same scenario occurs. If person A had to decide, he would always confess in this direction and he would always confess like this. And this makes sense. Both these arrows point towards lower years of jail, 2 to 1, 8 to 5. And from this, you see that everything is going towards this direction. In other words, we are going to the direction where both people confess. It's always in their best interest to confess. But the dilemma is, if you both confess, even though that seems to be in your best interest, it's worse off than being silent. So that's the entire idea of prisoner's dilemma. thing I want to do is just introduce some vocabulary because this is kind of important, is the Nash equilibrium. The Nash equilibrium is just defined as when no player can increase its expected payoff by changing its strategy. In other words, if you have a strategy and you change it, it can only get worse. And we saw in this case, the actual Nash equilibrium is in the bottom right. The reason it's in the bottom right is because if anyone changed the strategy, say A compressed and B was silent, B would now be worse. B would now be worse off. But same as vice versa. If one was silent, the other confessed, the one would always be worse off. Therefore, it's always in the best interest to both confess. So we have one Nash equilibrium over here. Now, let's actually compare Hawk versus Dove and Prisoner's Dilemma. We kind of saw that I wrote the arrows to show which strategies are better, and there's a star representing the Nash equilibrium. Does anyone want to comment on, in this case, the difference? In this case, the difference between the two games. Do the games look the exact same to you, or does something look different in terms of strategies to employ?
Yeah, I was just saying I think it looks. Wait, actually no. Yeah, it does look a little different because if you um go left to right, it doesn't trend to the right anymore. Like if you're a hawk, um, like it doesn't always trend to the right. I don't know how to explain that.
Yeah. So yeah, I'll explain this in more detail. But the really interesting thing is, looking at it, you think that the premise is the same. You're in a dilemma. Isn't it the same? Because a dove is like being passive, being silent. A hawk is being dove. It's always better to be a hawk, but sometimes you saw hawks and hawks don't vibe well, so you want to be a dove. So that's the dilemma. So looking at this, like the first time you might be look at it, you might be like, they're the exact same. But that would be wrong. There's a really important difference between the two games. And Krish was kind of talking about this. And the difference is the actual direction of the arrow changes. So actually, before I write this out, does anyone want to like have an idea of where do the arrows all show up? How do I connect it? And remember, I'm just going to recap this. The way we chose this arrow is like, okay, say in this case, person A was silent. Then the question is, what does person B do? Well, if person A is silent, well, then we have to compare which one is better. In this case, okay, B gets 1 year of jail, that's better, right? So in this case, you would move to the right. If person A was silent, it's B's best interest to confess. And we did it for every two players to get this arrow. Does anyone have an idea of how the arrangements or what directions all these arrows were pointing at the very end? So let's go through it. So, let's start with dove, and let's say person A does a dove. Okay, so in this case, they're doing one of these. In this case, it's in your best interest to play hawk because we can see 0.75 is a better payoff than 0.5. If you're a hawk versus a dove, you're gonna get all the food, so you might as well play hawk. And let's repeat the process. If person A played a hawk or had a more aggressive strategy, now it changes because hawk has a really bad payoff. What happens is it's in your best interest to play dove, which kind of seems interesting at the first glance. You might never have thought you would ever want to play dove, a more passive strategy. But it turns out that sometimes retreating from a fight over a resource is better than getting injured. And that's kind of the logic behind playing dove, even when the other person plays a more aggressive strategy. And now let's continue this. If we continue this, we're going to see that what we get is this cyclic pattern, where not even a cyclic pattern, where we have two strategies, hawk versus dove and dove versus hawk, that are pointed to two arrows. And these are a Nash equilibrium. Remember, a Nash equilibrium was the stage where no one would want to change the strategy. And of course, if you change your strategy, you would be worse off in either case. So now it's different because one, we have different amounts of Nash equilibria, but two, the directions of the arrows have also changed. And this kind of lends itself into a really interesting insight. We always, like to think that there's this debate between being selfish versus doing something for the good of the population. But the question is, in this scenario, there's no such thing as hawk being the optimal strategy, even though it betters dove. Because hawks are, hurt themselves by going against each other, it's actually in one's best interest to play the opposite strategy as the majority of the population. So let that sink in. Basically, if someone plays a hawk, it's in your best interest to play dove. And if someone plays a dove, it's actually in your best interest to play hawk. So what does this mean? Why did we get this 50-50 split, which we saw earlier, and how can we manipulate it? There's actually a mathematical way to go about this. And it's a really intriguing idea, but we can essentially assign scores to people's value. So the way we assign scores typically is say, okay, someone plays dove. What we're going to be like is, okay, if someone plays dove, these are, by the way, the payoffs. So they're going to be like, they get 0.5 for every dove they interact with, 0.25 for every hawk they interact with, and then you can repeat it for hawk. If you're a hawk, you get 0.75 for every dove you play with, and 0 for every hawk you play with. And all you have to do is just set this equilibrium scores equal, and that's actually how you calculate what the equilibrium concentration is. So earlier we was trying to see, what is that concentration? Is it 50-50? Is it 75-25? In this case, we actually got the scenario in such a way that it was 50-50. I just did the math out here, but it also gives you insight that you can use this to calculate it without even doing a simulation. In other words, I could just give you the game theory, values, maybe based on values and costs, come up with these numbers, and then based on just simple math, you can come up with what D and H is. The really insightful thing that you need to do for this is just write H is 1 minus D, because the hawk population plus the dove population will compose the entire population. And just doing that, one substitution basically allows you to actually calculate what the dove population and hawk population will be relative to the entire whole. So this is called, we got like D is 0.5, which means D is now the percentage of dove population. So it's 50% of the total population. Hawks are 50% of the total population. And this over here is called an evolutionary stable strategy, or ESS. Every solution to these pairs of equations will yield an evolutionary stable strategy, which will match the equilibrium we got in our simulation every single time, which also explains why food never actually influenced the equilibrium. It would only change the initial sense, because that changed, like we saw, the curves are really different at the beginning. But every time at the end, the equilibrium was always the same, because only the game theory principles lent it to the same solution every time. And I kind of want to end the hawk versus dove simulation on one note. And that note is, what does it really teach us? Why did I cover this out of all the different simulations I could? One is it gives us insight into the population dynamics and the expected frequencies of strategies within a population. The other is it lends insight into the question whether species act according to the selfish genes or to the good of the species. Remember, we were talking about how aggressive seems to be correlated with selfishness. But in this scenario, we find an interesting observation where being dove doesn't always mean you're not selfish. In fact, when the other person plays hawk, you would be selfish to play dove. It is in your best interest to do the opposite strategy, which is really intriguing, because that means selfishness can go both ways. You can be a dove and still be selfish by doing the opposite that other people are doing, but you can also be a hawk and be selfish by doing the opposite that other people are doing. So this idea of being selfish actually applies both ways, and it's like not only associated with being aggressive. At the same time, like we covered earlier, there are limitations of this game. We saw that resources were shareable, but the problem is, in the real world, resources are not always shareable. And that raises a new question that we haven't actually covered. I know the next few slides I'm going to go by pretty quick. They don't involve a simulation. But the question here is, say we change the game. Say no longer the resources were shareable. In that case, doves could not share resources with other doves. Now the question is, what do we do? Or are pure hawk and dove strategies still effective? Does anyone want to comment on that? What do you think a good strategy is when the resources are no longer shareable?
I think doves, because so wait, what do you mean by not shareable?
So say in this scenario, thank you for the clarification. In this scenario represented, doves could share the resource, right? That's why they got half and half, right? But say you could no longer share the resource. It's a 1 and a 0. Does that make sense? What is the optimal strategy anymore?
Oh, so you mean so it's all in. So like either you get it or you don't.
Yeah.
Oh, I think hawks then, because then they're more aggressive and they get the whole share.
Yeah.
more.
So yeah, that most people's mind go to. They think, okay, now it's much more prisoner's dilemma like. It's like, okay, now being aggressive has its, value. This time it's all or nothing. You always want it all. I mean, the same problem applies where if you want like two people go all in, it's bad for them. But the interesting thing is both strategies are equally bad. By changing like the one fact that resources are no longer shareable, it completely changes the dynamics of the game. And let's think about why, because that's kind of important. Pure hawk strategies don't work since non-shareable resources result in a high cost of injuries slash possible death. So to give you an example, because I'm saying non-shareable resources, this might be like a house, finding a house or finding a mate. You don't typically share those things. So in that case, it's a non-shareable resources. And if two people are say like competing for a mate, it's likely that there might be a high cost of injury or death. Similarly, pure dove strategies don't work because of a different reason, and that just means they no longer can split resources amongst each other anymore. So is there a point in being passive? And the question I wanted to pose is, what strategy would you guys employ? So you kind of understood that hawk strategies have the cons, dove strategies have the cons. Is there a better strategy to employ than both that we haven't been perhaps thinking about? Or do you guys have any ideas of strategies you might employ to get around the fact that the other two have cons?
Maybe we look at maybe you look at who you're fighting. Like if there's a dove there, um, or if there's no one there, then you take the hawk like approach. But if there's
I really like that. I really like that. So what Krish is getting is an approach called the bourgeoisie approach, or sometimes like the detective approach. So there's actually I'll say an infinite number of strategies, but each strategy has its own set of pros and cons. There is value in actually seeing who you're playing against and making a decision. Sometimes those approaches are called bourgeoisie, which we're actually going to cover in a bit. But surprisingly, the most common form of strategy in response to these situations, if you think when two, in this case, when two individuals are competing for a mate, it's not a bourgeoisie approach. It's something you wouldn't often think about, but it's a really interesting scenario. And this comes to a new game called the Wall of Attrition. And the approach that I was trying to hint at was the bluffer strategy. Now, the bluffer strategy is really interesting because it simply means the longer one waits, the more costs they accumulate, and the last one stand wins the value of the resource. Think about like rituals, like ritualistic fighting, etc., where you're trying to bluff the other person into thinking you're stronger. And the costs here are more of like costs of unresolved engagement. Typically, like in ritualistic fighting, you're not actually fighting the other person. Yes, there's a chance that you can get injured, but it's more like the longer one stays. Well, one, like if you're competing for mates, if you're going against someone, you have a less chance of pursuing other mates. At the same time, it's a mental battle, etc. So those are all different costs of unresolved engagement. So the interesting component at play is time. Here you're using time to your advantage. Now, I guess I should say that in theory, the bluffer strategy, the optimal way to play the bluffer strategy would be, take how long your opponent is willing to spend to get that one house, that one mate, and then add like a delta to it, right? If they're willing to spend an hour pursuing that resource to stand their ground, you can spend an hour and 1 second and win that fight because then you go home with that home. But that's not how life works. If you could just add a delta based on how other people are playing, that would mean you're a god. But that's not how like life works. Because then, okay, someone's spending 1 second, you could spend 2 seconds. The other person will spend 3 seconds. So that's where the bluffer strategy comes into a hazy zone. And it's really interesting because evolutionary game theory mathematics literally leads to an optimal strategy of timed bluffing, which to me I found pretty interesting. But I'm just going to show how it kind of works. So you can actually model the how time bluffing works using this equation. And essentially the overall, the overall thing that I want you to take away from this is that in this case, this strategy, well, actually, I'll go back here. In this strategy, you can kind of see that the higher the value of a resource, so in this case, the higher the value of the resource, people tend to wait more for that resource. In other words, you can see the curve shift. And remember, less people are willing to crit if the resource is higher. And this kind of makes sense. If the resource is worth more, you're willing to spend more time pursuing it. So this is something we actually see a lot in nature, but it's really cool because you can actually model it based on just evolutionary game theory mathematics to come up with this equation. Now, I actually didn't show how I derived this equation. I just put it out there for the sake of time. But it's really interesting because it actually allows you to do two things that I'm going to be talking about in the next two slides. So actually, I'll just go straight to it. We learned that greater values of resources result in greater waiting times, which makes sense. You're willing to accumulate greater costs for greater rewards. But the really interesting thing about the wall of attrition is you can understand the ratio of value and cost of specific resources by observing their interactions. Think about it. If you wanted to understand how valuable a home was to a creature, that doesn't make sense. Like, how do you do that? How do you even quantify that? It seems unapproachable. But by looking at the timing of disengagement, when you can actually reverse engineer the equation to calculate C over V based on the curve you kind of get in nature, and it gives you insight into how valuable individuals perceive certain resources, how they perceive the costs with those resources. And those are things you might think is beyond the scope of anything, like understanding how an individual perceives the value of something. But it turns out those things are mathematically reflected in how they interact with different resources, which is why game theory can sometimes be interesting, because you have that ability to reverse engineer to yield insight into aspects like value and costs without just by observing nature and then using a mathematical model. Krish mentioned this earlier, but the bourgeoisie strategy was essentially a strategy that kind of takes advantages of asymmetries. It's often this strategy associated with being very observant. Say you gain a possession of a resource before an individual comes along, you might be more inclined to play a hawk because you want to be more aggressive, because you already have like that domination, like you're on that resource first. But say you came along later, then you might play dove. So there's ways to actually change the strategy you play based on how you observe your surroundings. So in this case, you can kind of see, I don't know the animal, but it's guarding its house using the bourgeoisie strategy. It's going to be more aggressive when it's getting that house because it already has possession before another individual comes along. And lastly, I just wanted a few takeaways, like what did we learn from all of this, aside from, simulations are a great way to envision everything. Evolutionary game theory helps us understand why certain biological strategies appear commonly in nature, especially the intuition behind why they have arisen. And lastly, it kind of shows that biology and mathematics are not really mutually exclusive, because it's really nice to use a quantitative lens in mathematics to explore a qualitative science in biology, because by using math, you're essentially able to quantify stuff in a way that allows you to perform simulations, allows you to perform experiments, allows you to see things like value over cost, and then use your qualitative observations to see what's happening in terms of cost and value. So that's why using evolutionary game theory can kind of lend a lot of insight into the structure of biology. Yeah, and with that said, that concludes lesson on evolutionary game theory. Do any of you guys have any questions about anything we covered so far? Okay, that sounds good. I'm going to stop the recording now.